All right, we're on section 2.2 with differentiability and how f prime might fail to exist. Well, one way that f prime or the derivative might fail to exist is at a corner. So this is a corner. Another place is a cusp. So you can see a corner, it goes straight to the corner. With a cusp, it kind of curves to that point. So this is a cusp. Now, we don't have a tangent line there, and so we don't have a derivative. I mean, we could draw a whole bunch of tangent lines. So instead of saying we have an infinite amount of tangent lines, we say we don't have a tangent line there. So we say that the function is not differentiable at x equals 0 in this case. Same thing over here, not differentiable at x equals 0. Sometimes we have vertical tangent lines. So you can see there's a vertical tangent line here at 0. Now here's the tangent line here. Whoops, I missed a little bit here. Then tangent line here. And as we get closer to 0, the tangent lines are getting more and more vertical until we finally get to 0. And that is a vertical tangent line. So we say that the function is not differentiable there. And then finally, at any discontinuity, so any discontinuity, so you could have like a removable discontinuity. There's no derivative there. The function is not differentiable at any discontinuity. So it could be a vertical asymptote also, not differentiable there. Find where a function is not differentiable. Find all points in the domain of f of x where f is not differentiable. So let's look at, let's look at the graph of this. So here's absolute value of x. So minus 2 means right 2, and plus means up 3. So we're going to take that, we're going to go right 2 and up 3. So let's say right there. So that's the new vertex. So at 2, this function is not differentiable because there was a corner there. So the answer they're looking for is at x equals 2. Differentiability implies local linearity. So if you look at the window here, they're talking about this point about right here. Now, if you draw a tangent line and then you zoom in on it, maybe it's the point right there, the curve is getting, well, this would be letter B and this is letter C. So the curve is getting more and more straight. Now, why would we care? Well, later on, we're going to use this point to approximate this point. Now that's a pretty good difference there. So we want to stay very close to the point of tangency. So if you use this point to approximate that one, that's not very good. So the closer we can stay to the point of tangency, the better our approximation will be along the tangent line. So if we have a tangent line here, we use this point to approximate that one, that might be pretty good because we're staying close to the point of tangency. But that's really later. But this says differentiability. If a function's differentiable, then it's locally linear. Let f of x equal the natural log of x. Use NDER to graph y equals f prime of x. Can you guess what function the derivative of natural log is? So we're trying to maybe identify what the derivative, I don't know what all this is. Oh yeah, this is clear. What? Gotta see, I'm writing on my laptop and sometimes my wrist will make things pop up there. So we're going to go y equals. We're going to do math, and number 8 is derivative. We're going to do the derivative with respect to x, so we'll hit x there. This is the natural log of x, and we're evaluating everywhere. So when we go zoom 6, it's hard to see, but this is the graph of 1 over x. So we can say that the derivative of natural log of x is 1 over x. Differentiability implies continuity. So if a function is differentiable, then it is also continuous. So we say if f has a derivative at x equals a, then f is continuous at x equals a. The converse of theorem 1 is false. So if it's continuous, it's not necessarily differentiable, and we see that with cusps or corners. It is continuous there, but not differentiable. Compare the right-hand and left-hand derivatives to show that the function is not differentiable at point P. So we're saying the function is not differentiable at point P right there. So we're going to do the limit as h approaches 0 from the left of this function right here, which the function is just 2. So when we plug 1 plus h in there, it's just going to be 2. And then when we plug 1 in there, it's going to be 2 over h. Well, that's 0. So the left-handed limit is 0, and that's a horizontal line. And a horizontal line has a slope of 0. How about the right side? Limit as h approaches 0 from the right. Well, now this function is 2x. We have 2 times 1 plus h minus 2 times 1, which is 2 over h. So that's the limit as h approaches 0 from the right of, we'll have 2 and 2h, but 2 minus 2 is 0, so we have 2h over h. Well, the h's cancel, and 2, and 0 does not equal 2, so the function is not differentiable at 1 there. Now we'll do the same thing for number 4. We have the limit as h approaches 0 from the left. And this function is y equals x. So 1 plus h minus f of 1 would be 1 over h. The 1's cancel, and the slope is 1. And yeah, we know that the slope of that line is 1. But now what's the slope of 1 over x at 1? Well, let's find out. Limit as h approaches 0 from the right of 1 over 1 plus h minus 1 over 1, which is 1 over h. So we have the limit as h approaches 0 from the right. We got to multiply everything by 1 plus h. Everything. So that'll be a 1 minus 1 plus h over h times 1 plus h. Well, the 1's cancel, and we're left with negative h. Limit as h approaches 0 from the right of negative h over h times 1 plus h. H's cancel, and so we end up with negative 1 over 1 plus 0. So we end up with negative 1. So 1 does not equal negative 1. 1 does not equal negative 1. So this function is not differentiable at 1. At what domain points does the function appear to be differentiable? So for number 6, it's just a nice smooth curve. So all values, it's differentiable. B, continuous but not differentiable. We're talking about corners and cusps. We're continuous there, but not differentiable. So none for this one. There are no corners, no cusps. Ooh, man, I don't want to open that. C, neither continuous nor differentiable. And that's discontinuities. So that one's none also. B, A, differentiable. So negative 2 to negative 1, union with negative 1 to 0, and then 0 to 2, and then 2 to 3. B, continuous but not differentiable. That's corners and cusps. So X, how's it not? Oh, that's not writing. X, come on, right for me. There we go. X is equal to negative 1. C, neither continuous nor differentiable. So there's two places where this is discontinuous. We have a jump discontinuity at 0 and removable at 2. So 0 and x equals 2. Number 10, differentiable. Negative 3 to negative 2, negative 2 to 2, and 2 to 3. So not differentiable at negative 2, not differentiable at 2. B, continuous but not differentiable. That's corners and cusps. X equals plus or minus 2. And letter C, neither continuous nor differentiable. That's discontinuities. So this one is none. Find f prime if f of x equals absolute value of x plus 2. Well, the absolute value of x plus 2 is equal to x plus 2 when x is greater than or equal to negative 2, and the opposite of x plus 2 when x is less than negative 2, because you're going to get negative values. When x is less than negative 2, you're going to get negative values, and what does absolute value do? It takes the opposite of negative values. So we want the limit as h approaches 0 of the function we're using. The function is, since we're at 1, that is greater than -2. So we are using x plus 2. So we have 1 plus h plus 2 minus 1 plus 2 over h. Limit as h approaches 0 of, that's going to be 3 minus 3, that's h over h, that's equal to 1. Now, the other way to look at this is the graph is over here at -2. There's the vertex. And over here at 1, the slope is 1. So another way to look at it. Now, that's, of course, not the calculus way to think about it, but if you can get that, if it'd be a multiple choice, that'd be fine. But this, this is calculus. So this is the calculus way to kind of answer it based off the definition of absolute value. Find the equation of the tangent line where the graph crosses the y-axis. So the graph crosses the y-axis when x is 0. So if we plug 0 in here, we get 0, -3. Now we need the slope. So limit as h approaches 0 of 0 plus h squared minus 3 minus 0 squared minus 3 all over h. Well, we love it when we have zeros in here. Limit as h approaches 0 of h squared over h, which is the limit as h approaches 0 of h, which is 0. So the slope is 0. So the equation of the tangent line is y plus 3 is equal to 0 times x minus 0. Or in other words, y equals -3. But you don't even have to write that. You could leave it like that right there. Evaluate limit as x approaches 2 from the left. Well, let's say that x is 1.99. 1.99. So on top, we get a positive number. And on the bottom, we're getting really close to 0. So a really small number, but a really small negative number. So this one would be -infinity. And I know that because there's a vertical asymptote there at 2. So over here at 2, we have a vertical asymptote, and on the left side, we're headed down to -infinity. Exercise 11 through 16, the function fails to be differentiable at x equals 0. Tell whether the problem's a corner, a cusp, a vertical tangent, or a discontinuity. So let's do number 12. We've got our calculator here. Not second, we want y equals. We'll clear this. Clear. X raised to the 4/5. And graph that, and we see we have, now this looks pretty straight, but there's actually a little bit of a curve to it. So this would be cusp. Let's clear that. 3 minus math number 4 third root of x, and we graph that. And at 0 on this one, we have a vertical tangent. And then the last one, we're going to clear this. Let's see, math number 4, math absolute value of x. And we're going to graph that. And I think we have a cusp there. So that one's going to be a cusp. Use derivative to graph the derivative function. If possible, identify the derivative function by looking at the graph. All right, so let's go, let's clear this. Let's go 0.25 x to the 4th. And when we graph this, oh, we got to do n derivative. We're not graphing the function, we're graphing the derivative. So math number 8 is derivative. We're taking the derivative with respect to x. So 0.25 x to the 4th. And we're doing the derivative everywhere. So instead of a nice value like 5, that would just give us a point. We're doing this everywhere. So we're going to put an x there. So we're going to graph it. And this is actually the graph of the derivative. And the graph of the derivative, hopefully you recognize it. y prime is equal to x to the third. And then the last one, we have math. And if I scroll down to number 8, we can see that it's derivative. And we'll be using 9 later, that's integral. But right now we're doing 8. We're taking the derivative with respect to x. It's negative natural log of the absolute value of cosine of x. And we're doing that at all values, at all x's. So when we graph this, y prime is equal to, that is the graph of the tangent of x. And I mean, we can let it finish there, but it's tangent. It takes a little slower to graph the derivative than it does the tangent because it has to do a lot more calculations to get the derivative at all those points. All right, there we go.